Alright class, let's go ahead and continue our lesson on hardware. We're going to go ahead and introduce memory hardware. If you remember the four components of computers, storage or memory, however you want to call it, is one of those components because we need to save the data for future usage, especially if we're solving difficult problems. It's good to have that data accessible. So there's two types of data we're going to be talking about, RAM and ROM. So first, what is computer memory? Computer memory is a collection of electronic components, it's hardware, that stores data and instructions for a computer to use. So memory, just like in humans, it helps the computer access data from the past and the present. Our memory serves us in so many ways, right? If we learn something, right, we can lean back on that learning, on those memories, to solve new problems. It's the same for computers, right? If they have access to historical data, they're able to solve difficult problems. And if we're talking about something like AI, right, it really, really relies on memory a lot in order to solve and really emulate, right, the intelligence of humans. Artificial intelligence, right, AI. So there are two main types of memory we'll be talking about, just like I mentioned. There's RAM or ROM. So RAM is called random access memory, and then there's read-only memory. So what is RAM? What do they mean by random access memory? So it's a type of computer memory that temporarily stores data, so it's not permanent. And this data is used by the CPU. This data is special because it's really made for quick access. So your CPU is for problems that you need to solve very quickly, and maybe you don't need that data to be saved right long term. So this memory is called volatile, meaning that when the computer is powered off, the data in the RAM is going to be lost. So once you shut off that computer, the RAM gets wiped. So how could this be useful, right? A memory that doesn't last very long. Well, when you heard when we're talking about RAM, it's useful, like I said, for operations and tasks that require speed. So if you're in a video game and you need to render the graphics, right? You need to show all the 3D models. You need to show all the colors, the textures, to make that game really pop, right? That's going to require a lot of RAM because we want that to show up quickly, and the computer doesn't necessarily need to remember, right? What the screen looked like 10 seconds ago, right? Now there's separate software, right, that might hold long-term memory, right, which we'll cover kind of in some of the next slides, where it needs to remember, right, what color is this map, or what color should this location in the game be. But as far as actually showing the graphics, we're going to be relying a lot on RAM. And if we compare it back to humans, right, where humans have multiple types of memory, we have our long-term memory. So those are memories of our family, right, of our loved ones, of experiences we've had growing up. But we also have short-term memory, right? Whenever you're cooking, right, maybe you're cooking a meal, you need to remember the recipe that you just looked at. You need to remember where you put the ingredients, right, which one you're working on. You're not going to remember all those details, 5 years from now. You're not going to remember that recipe word for word, unless you look at it many times, right? But you're definitely not going to remember those small details, right? Like when the meat is going to be ready, when the vegetables need to be thrown on the pan, right? That's you relying on short-term memory. Well, computers emulate that type of memory. There's some problems where we just need to store something very temporary, very quickly, so that we can execute the task a little bit faster. So when you're cooking, right, you got to be quick, so things don't burn on the pan, so things don't burn in the oven. What's the same for computers, right? There's certain tasks where we don't need to remember every single little detail forever. We just need a temporary place to put the data, and just like in this example, right, the video games. A good thing to know is when you hear the term just memory, usually it's referring to RAM. So although memory technically, right, is a term that should refer to all types of computer memory, in just kind of everyday use, especially around technical people, when they just say memory, they're probably talking about RAM. So now there's ROM, right? So this is when they're talking about storage. So kind of distinguishing the words, right? Memory is usually RAM. When you say the word storage, you're usually talking about ROM, read-only memory. And we'll also talk about some different types of storage in the next slides. But yeah, so different from RAM, we have ROM, or read-only memory, which is a type of computer memory that permanently stores data. And like I said, it's usually called storage. So this is non-volatile. So remember, volatile means you turn off the computer, it all disappears, right? For ROM, this is not the case. When you power it off, that data is still going to be there. In fact, ROM is called read-only because the data you write to that hardware, to that physical electrical component, is actually usually permanent, meaning you can't change it, you can't add. So read-only means you can only read the data that's on there. You can't write new data, and you can also modify it. It's read-only. You can't do anything else to that data. So why do we have ROM? Why would we have some data that's permanent in the computer? And this is different, right, than you saving your files, your photos, which again we'll cover in the next slides. This is a very, very special type of memory that the computer relies on for operating system level data. So if you remember operating systems, it goes in the middle, right, between the hardware and your software. So you're on your video game. The video game needs the computer to provide a certain amount of power to show certain pixels on the screen, to handle all the different inputs from the controller. Well, operating system sits in the middle, right? Operating system is what controls all the physical components. Otherwise, all that metal, all that electrical technology, it's just sitting there, right, and doesn't know what to do. So for all those rules for the operating system, you actually save them here in the ROM. The ROM is responsible for storing all those essential functions. How much power is just enough, right? What is too much power? If the computer gets hot, right, turn on the fan. So all those very, very specific rules that never really change, they're going to be stored in the ROM. So this is not, like I said, to be confused with some of the different type of storage where you typically put your personal data, right, documents, photos, music, etc. We'll be covering that type of storage in the next slide. So this type of storage you can't change. It has all the instructions the computer needs to function properly. So of course, the memory we're more used to is secondary storage. So what is storage hardware? So the memory where most users typically read and write their files to is called secondary storage hardware, or a secondary storage system. So secondary storage is extra storage, right? So it's a type of computer memory where non-critical data that doesn't need to be accessed as frequently as primary storage is stored. It's also known as auxiliary storage, which is just a fancy word for extra storage. So like I said, here you can read and write data. So write means you can add new data. You can actually write, if it was a piece of paper, you could write on it. And you can also read that data, right? You need that document that you saved a few weeks ago. You can go in there and read it. You need to add a new document. You can go ahead and write to that data, to that storage. So you can have photos, music, videos, right? Whatever your heart desires. So this is also non-volatile, right? It'd be terrible, right, if every time you turned off your computer, all your important memories, documents, photos disappeared from the computer. So this is non-volatile, meaning when you do turn it off, everything is preserved. It doesn't disappear like in RAM. So RAM is the only one that's volatile. And remember, that's useful because you really want, RAM is really for those quick operations. So you don't want to fill up the RAM, right? So that you can do things quickly. So that's why it's good for RAM to be volatile. And so some examples of secondary storage hardware. So before we go over the examples, just a word we've been using a lot, but it's important to define it, is the word file. So file is a collection of data or information stored on a computer. So anything that you store, that you put into storage, into computer storage, is going to be called a file. So yeah, as we've discussed before, files can store all types of data, right? Again, documents, text documents, photos, music, video, whatever you can imagine. So some common storage hardware that might be familiar with is hard drives. So your computer, right, it might have a hard drive in the magnitude of gigabytes. Some really fancy computers might have terabytes, right? Maybe you built your own computer, right, and you wanted extra memory. You go to the terabytes kind of levels. But for the most part, hard drives will be in the magnitude of gigabytes. Your phone, right, has secondary storage. My iPhone, for example, has 128 gigabytes, which is usually enough for all my pictures, apps, right, app data, and so forth. We have USB flash drives, not as common anymore because of the next example, cloud storage. But yeah, USB flash drives, they used to be very popular. You needed to move your data from one computer to another. You needed to, have your presentation ready to show in class. You'd put it in your USB flash drive. You'd take that USB to class, plug it into the classroom computer, right, and then boom, your presentation would show up. So that's more recently been replaced by cloud storage. So now there's services where your data is stored in data centers, right? So it's not living up in the cloud. There's not a cloud floating up in the sky holding all your information. These are actual physical data centers. They have physical storage hardware. And if you remember servers, they have those types of computers so that you can request your data and the server will serve up your data whenever you need to access it. And then, of course, input and output hardware, some very, very important hardware that makes computers easy to use. If you remember back in the very first computers, there was not a lot of input-output hardware. You would load up these cards, these punch cards, to tell the computer what to do, and it would give you a punch card back. So only like really specific domain experts could even read those cards, right? The average person, that was just nonsense. Well, now we've added all these different types of input-output hardware. Some of them have been revolutionary and made computers way easier to use. So input-output hardware, what the heck is that? Well, I/O hardware refers to the physical devices that allow a computer to interact with the outside world by inputting data into the system and also outputting data from the computer system. So they also can enable communication between computers, right? There's network hardware, your Wi-Fi routers with your computer's network adapters. They work together so that you can connect to the internet. So input and output devices do make computers easier to use, and they make the information more accessible, right? Before we had those black screens with green text, and you had to type in commands, right? Now we have all sorts of ways, our keyboard, our mouse, touchscreen. We'll be covering some of those different input-output devices in the next slides. So remember, information is data that has been processed and then transformed into a more useful form. A little bit of quiz 1 question there. So input-output hardware, here are some examples. So on the left we have input, on the right we have output, and there is some overlap, right? Some devices provide both input and output. So keyboard input, you type in or you push on a button on the keyboard, you press on one of the keys, and it corresponds to a letter, sometimes commands, all sorts of things, right? You can even combine keys together to do special operations. For those of you who are still getting used to computers, some commands that you can execute. For example, input-output hardware. If I highlight this and I hit Control-C, if I'm on a Mac, Command-C, I can copy the text and then I can paste it elsewhere. I can go here and paste it. Oh, didn't copy the right one, so Control-C. And then I paste it right there. Hardware, there you can see it. I can paste it here as well. See it again. There you go. If I hit Control-Z, it'll undo that. Oh, I actually moved my title there. I'm going to hit Control-Z again, and it moved my title back. So yeah, you can combine these keys together, and the more you know the keyboard, the more agile you can be on the computer. Some people are extremely fast with the keyboard, right? For example, court reporters, they have special type of keyboards that enable them to write almost word for word, right, what people are saying in a courtroom. And their job is to record everything that happens in the courtroom. Let's see, let's make this big. And then we have our mice, right, the computer mouse. Here are some other examples of pens, joysticks, right, if you're using special types of video games, scanners, right, to read our documents, barcode readers, that is an input device. It scans that barcode, which is a very, very revolutionary technology. The guy who made that became rich out of that technology. And simple, right? Those little lines, the barcode scans it, and then it gives back to the computer information on what that item is. We have headphones for output. They provide us with audio output. We have screens for visual output. Printers for physical output, right, that we can hold on paper, usually with some kind of ink. Speakers, right, for more audio output. And then we have some in the middle, right? Touchscreen. You can provide input to the touchscreen, so you use your finger, swipe, all that stuff to tell the computer what to do. And then, but it also works as a screen, right? Just like on the right, where it's providing information on the application you're using. And then we have some older ones, CD, DVD. You could read, meaning you can output data from the CD. You could also input data into the CD, like you could save information. So also an example of external or secondary auxiliary storage. You have the USB, sometimes called a pen drive. Just a few other examples here. Some of them not so popularly used today. So I have two videos for us today, a little bit interesting on some hardware that we use every day and just about how it works, how it came to be. So one that I thought was always interesting was the QWERTY keyboard, right? Why isn't the keyboard in alphabetical order, right? Why is it in this very particular setup? Let's go ahead and watch the video.
I knew I was underwater. I just didn't realize I was this underwater.
Why does every keyboard look like this? The QWERTY keyboard is overrated. Okay, so this top strip here, there is a 99% chance that on your keyboard, it's QWERTY, QWERTY.
Yeah, so not every single keyboard in the world is QWERTY, right? There are special keyboards out there for special uses, but for the most part, for most of our PC users, personal computer users, we're going to be using the QWERTY keyboard.
We all have these QWERTY keyboards. There's probably even one in your pocket on a screen. But why? Why is this pattern of letters so familiar?
This, of course, is the keyboard.
But why, of course? QWERTY was just one person's invention from the 1870s. It's almost 140 years old, yet it's still the standard.
All of these machines are alike in many respects.
We all use it but don't know why. That's the definition of overrated. And it turns out that this little keyboard is the subject of intense debate, some lies you've probably been told before, and a few real explanations that might surprise you, including an old-fashioned cartel. Lots of people have tried to arrange these jumbled letters. There was a half-century period of indecision, debate. In the 1840s, Hughes Printing Telegraph arranged the keys like a piano keyboard. Or look at Hanson's writing ball from 1865.
Yeah, just like most technologies, right? They were always a work in progress. The first one that came through, right, wasn't the one that we use today. And that's a testament to like anything in life, right? You're not going to always get it right the first time, but every time you give it a shot, right, we get closer and closer to the ideal, to the best thing. So yeah, just like the keyboard, right, we had some really, really strange iterations across history. I can't imagine using this thing and trying to type up an essay on it.
People's fingers pecked at this thing. The letters varied per version, but they showed up in this pattern. This 1868 typewriter looks weird too, but it was the start of something. The inventor was Christopher Latham Sholes. He looked like typewriter Santa Claus.
Yeah, so he had his first invention, right? In terms of keyboards, kind of looked like a piano, right? Like a, musical keyboard, more than the one that we use today.
And he kept going. In 1870, he developed a pattern like this. As of 1873, he'd come up with a keyboard that looked a lot like QWERTY.
Yeah, so his life's work was keyboards, something we probably take for granted every day. Someone spent their entire life innovating them.
But there were quirks. Notice that period where the R should be, and the A and Z are flipped. The M also sits next to the L. Remington, a company that made machines for shooting and sewing, bought the design. Suddenly, they were in the typewriter business. The design Sholes patented in 1878 was basically QWERTY. Along with the numbers, the only weirdness is that M next to the L and the C and X are flipped compared to a contemporary keyboard. The company that made Remington typewriters was soon sending out sales packets with the QWERTY we know and love. But that doesn't quite explain how QWERTY got big. There are urban legends. Ones that QWERTY was designed that way to keep typewriter keys from jamming. But lots of designs could do that, and there's not a lot of good evidence that that's why QWERTY was designed. Other options were even still around in 1890, like the Merit typewriter. You moved this handle to the right spot for your letter and pressed down. The letters weren't in QWERTY, they were in a big long strip that looked like this. So it was a Kupich keyboard. Many typists believed it worked as well as QWERTY, but the best evidence of all that QWERTY wasn't the perfect design might be this invention from 1889. The keyboard? Not QWERTY, but Expuncture. The inventor? Christopher Latham Sholes, the guy.
Yeah, so the same person responsible for QWERTY actually kept innovating. He kept trying to perfect the keyboard, and QWERTY was not his last iteration. He had different versions come much after QWERTY.
Guy who invented QWERTY. He created it just before he died. Even the creator of QWERTY wasn't settled on QWERTY. And that's where the cartel comes in. Look at this king. He has something to do with QWERTY. See the label on his crown? Trusts. In the 1890s, many companies merged into trusts that allowed them to fix prices and control markets.
Yeah, this era is actually where the game Monopoly was first based on. So this was a time when entire companies were becoming excessively large, right, and were deciding prices, winners and losers in the economy. Yeah, it was out of control. So just fun fact, that's where Monopoly came from.
In 1893, that happened with typewriters, when some of the biggest manufacturers came together to form Union Typewriter Company.
So yeah, this as important as not important as it seems today, right? There's an entire economic war going on just related to keyboards back in the late 19th century, early 20th century.
Manufacturers cared most about price and technical improvements, like how the typewriter worked. But there was another effect of the trust. The biggest company made Remington typewriters, and they used Sholes' QWERTY keyboard design. The trust did the same. Most experts think the trust didn't work to fix prices. It had trouble beating innovative competitors, but their market power did fix a pattern on the keyboard.
Yeah, so QWERTY wasn't the best, but the company that chose QWERTY, that chose to put QWERTY in their typewriters, was the best, was the strongest company. So it didn't matter if there was better keyboards coming along the way. They couldn't compete economically with that company because it was a monopoly at the time. And funny enough, the company was a gun company.
And there's one more reason why that pattern stuck. Look at these old typewriter ads, or these early typists. Now you might notice that most of these students are women. That is worth noting, but for the story of QWERTY, it's more important to notice that they're in a class, together. Typing wasn't like it is today, where you get one of these at the office or one of these when you're born. Typists trained. They took classes. If you took a class, you took it for the most common keyboard. That was QWERTY. People still debate whether QWERTY's the best. Some say the 1930s Dvorak keyboard is better. Others say it too is overrated. Whether it's the best system or not, QWERTY isn't going anywhere anytime soon.
How you type is more important than what you type. This is the mark of a good typist.
Yeah, so just evidence that sometimes the reason we do things today, the reason things look like they do today is not because it's the best. It's just because that's what we got used to, right? Who's to say, though? Maybe in the future, right, we transform the keyword again. We're already transforming input in general, where we're moving away from these, clunky keyboards and mice, and we're moving on to something a lot more compact, and that can do all the things that these different I/O devices can do, and that's the touchscreen.
There are so many other
So yeah, let's go ahead and look at a video on one of the most widely used input-output devices, the touchscreen. Let's see.
I need to find the best way to learn math and science.
It's brilliant.org.
Whoa.
In 2010, South Korea experienced a particularly cold winter. People couldn't activate their smartphones while wearing gloves, so they began
Oops, let me get rid of that.
wielding snack sausages, causing one company to see a 40% rise in sausage sales. So, what could sausages do that gloves couldn't? In other words, how do touchscreens actually work? In 1965, the first ever touchscreen was invented to help British air traffic controllers efficiently update flight plans. However, the technology was too unwieldy and expensive for widespread use.
Yeah, as powerful as computers are, right? Just as important as those CPU components, as those storage components, are also these input-output devices, right? Because if the computer isn't easy to use for whatever task that is at hand, then what's the point, right? So that's what output devices do. They do help the computer be more useful.
Over the following decades, engineers further developed this technology and experimented with alternative kinds of touchscreens. Soon, resistive touchscreens dominated the market. But then, in 2007, Apple released the first iPhone. It was a breakthrough, yet it functioned using the same principle as the first touchscreen: capacitance. Nowadays,
Yeah, the idea of a touchscreen being able to replace all the buttons on our phone was crazy. There were already touchscreens, right? But they're going to cover why some of these early touchscreens weren't that good, and definitely not good enough for us to fit on such a small screen and do all the things that it can do.
capacitive and resistive touchscreens are two of the most common types. Both use an external
Yeah, so notice resistive here on the right. That's something you might see like on an ATM machine like they have in the picture, and then capacitive, that's what most of our smartphones use today. Some very, very, very early smartphones might have used resistive. But yeah, notice the frustration on the resistive side, right? Resistive is a little bit clunkier, and we'll see why.
resistive touchscreens are two of the most common types. Both use an external input to complete their electric circuits. In conductive materials, electrons flow around atoms, forming an electric current.
Yeah, just like everything in computers, it deals with electrical currents. That's how the inputs are read.
In contrast to insulators, the electrons in conductors are weakly bound and flow easily. A resistive touchscreen has two layers. The top is a clear, flexible material, usually plastic, while the bottom is something rigid, like glass. These layers are coated with a conductive substance and separated by a thin gap. When something pushes hard enough, the layers connect.
Yeah, that's why those older touchscreens, you really had to push very, very hard sometimes, especially if it was like an older screen, right? It would wear down. So in order to get that connection to be read, you really had to physically bend the screen.
completing the electric circuit. This
So yeah, once the two screens touch together, then boom, the computer could read the signal and say, oh, there was a touch here, right? Somebody pushed on this area of the screen.
causes a change in voltage that the machine's software reacts to. Resistive touchscreens can be a little unresponsive, but they're generally cheap and durable.
Yeah, again, not very responsive because you have to actually bend the screen with your finger. Which seems like not that difficult, right? Just a piece of plastic, but when you're trying to fit a lot of information on the screen, maybe it doesn't go exactly right where your finger went.
So they're favored for industrial or mass use. A vast majority of the touchscreens produced in 2007 were resistive, but in the years following the iPhone's release,
Yeah, so we had resistive touchscreens first, right? Those were the clunky ones. And then iPhone comes out and boom.
most became capacitive. Individual models vary, but smartphone touchscreens today typically consist of a protective insulating glass exterior and an LCD screen at the bottom that produces the images you see. Between the glass exterior and the LCD screen are several sheets. One is lined with rows of a transparent conductive material that carry an alternating electric current. A thin insulating layer separates these conductive lines from others that are arranged as columns. One on top of the other, the lines form a grid. The points where they intersect are called nodes. The phone's battery draws electrons along the first layer of lines, and some electrons accumulate at every node, creating a small electric field. These screens are called capacitive touchscreens because the nodes act like capacitors by storing charge. They're generally easier to use than resistive touchscreens because they interact directly with your finger without the application of force.
Yeah, so you no longer have to bend the screen. It's actually storing the charge. Now, where is that charge coming from?
Your body is a great conductor and is constantly transmitting electric currents. Why? Because about 60% of you is water. Now, while chemically pure water is an insulator, most water is impure. The water inside you is loaded with ions, atoms or molecules that have a net electrical charge. So when you click on an app, your finger functions like a third electrical line. It interacts with the existing electric field, which induces a weak electric current that travels through your finger and eventually back into the phone.
Yeah, so your finger, your body acts as a conductor of electricity, right? We are conductive. It's the reason, right? If you ever have been shocked by maybe some static electricity, right, accumulated on your laundry, or if you've had the unfortunate situation of getting electrical charge, right, from a socket. The reason that the charge goes through is because we are conductors. We do conduct electricity, and it does have to do with our bodies being mostly water and all the ions that are in the water. So yeah, that actually works in our favor when it comes to touchscreen technology. Because we're able to conduct the current, we're able to interact with the electrical currents on that screen.
This changes the amount of charge at the affected nodes, and voltage measurements along the second layer of lines tell the phone's microprocessor which part of the screen is being touched.
Yeah, so remember, microprocessor, that's actually the CPU, the central processing unit. That's the one that's going to receive those input signals and interpret them and say, there's a lot of voltage on this area of the screen. That means that's where we received the touch. And again, you don't have to bend the screen like we did before.
However, if you try using a smartphone while your hands are wet or gloved, you'll probably have some trouble. Both interrupt the electrical connection between your finger and phone. If water is splashed across the screen, it might trigger many underlying nodes, and the phone could act like you've touched it in multiple places at once. On the other hand, gloves are insulators, so the charge has nowhere to go. Meanwhile, objects that conduct electricity about as well as your finger, like banana peels and certain processed meats, can all activate the screen. Knowledge that can come in clutch when you're in a pickle. Another new technology that feels like it was lifted from the pages of a sci-fi novel.
Yep, so touchscreens, just a little bit more about how they work. It's all electricity, just like computers, right? That's how they interpret data, on or off, really high or low voltage. That becomes zeros and ones, and that can become pretty much anything we want. Could be a touch on a screen, could be music, whatever our heart desires. So that's it for week 2's content. Make sure to complete lab number 2, get that started this weekend. And as always, keep an eye out for discussions, homeworks, and if you ever need any extra assistance, accommodations, feel free to reach out via the Canvas inbox. Have a great weekend, y'all. We'll see you next week.